Assalamualaikum and hi. In this video, I will explain how pressure drop affect process piping system. In this illustration, okay, it shows an example of pressure drop where there is different between 2 points in the pipe. Okay, it is common that pressure drop or pressure loss happens when a liquid enters one end of the pipe uh, and one end of the pipe of a piping system and then leave the other end of the pipe. As an engineer, we need to know how to calculate pressure drop in a piping line because by knowing the pressure drop, we can determine the suitable pipe diameter, pump specification, pumps or motor size, and valve types. Pressure drop also determine the overall system, okay, pressure head, overall system pressure head requirements. With all this information, we can properly design a system. Okay. If the pressure drop is high in the pipeline, more amount of energy needed, okay, to maintain the desired process flow. Uh, Thus higher horsepower motor is required. Okay. But if the pressure drop is low in the pipeline, less energy is needed. Thus, lower horsepower motor is required. Important to note that if the piping system need too large head to overcome a large pressure drop, this can give a bad effect on components within the system. Pressure drop can be affected by the product properties, including density, heat capacity, temperature, and viscosity. Mechanical components in piping system can also affect pressure drop, such as valves, flow meters, adapters, couplings, and tubing. These components remove energy from the process flow. Mechanical pressure also can affect pressure drop. This include the cross-sectional area, the pipe interior surface roughness, the length of the pipe, the number of bends in the system, and the geometrical complexity of each component. Change in elevation of the piping system can also affect pressure drop. This is an example of equation from this website, CSI Design. A simple equation and quite easy to understand. Okay, the equation used to calculate the pressure drop in the process piping. So basically, uh, 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 it uh, it how to say from this equation it shows that pressure at the end of the pipe can be related, okay, that is equal to pressure at the start of the pipe, and then we need to minus with friction loss, minus with fitting loss, minus with component loss, plus elevation between the start and the end of the pipe, plus pump head. So the elevation between the start and the end is actually elevation at the start of the pipe minus the elevation at the end of the pipe, and then the pump head is equal to 0 if no pump is present. These equations can also be used to calculate pressure drop, but basically this equation is to calculate pressure drop with a friction, pressure drop due to the friction. Okay, so the friction factor inside this equation is a function of fluid flow rate, fluid density, viscosity, pipe diameter, pipe surface roughness, and pipe length. So friction factors is dependent on the Reynolds numbers and pipe roughness. Okay, from these properties. So if we know the pipe roughness, okay, if we know the pipe roughness and we can calculate the Reynolds numbers, we can use this chart. Okay, this chart is to find the friction factor, and this chart is known as friction factor or Moody chart. Pipe roughness in this chart is actually a relative roughness. So let's say if you get data of absolute roughness, you need to convert the absolute roughness to relative roughness by using this equation. So basically you need to divide the absolute roughness by piping inside diameter. This table is a shortlisted material. Okay, this table showing a shortlisted material for pipe roughness, absolute roughness actually. Right, it's just a short list by this textbook, Towler and Sinnott, Chemical Engineering Design Principles. If you would like to know more details on the pipe roughness for other material, you may refer others handbook, such as Paris handbook. All right. Okay, and this is another commonly equation to calculate the pressure drop, where friction factor in this equation it substitute with coefficient of friction. Okay, this coefficient of friction. This is relation of coefficient of friction, okay, and can also be substitute with this. Coefficient of friction is also known by this relation. Okay, the R. Sorry, I forgot to type to type the R definition. So let me write here. So R. Sorry. I have difficulties to find the point of my pen. Okay, this R. Okay, R is shear stress. This R is a shear stress at 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 the pipe wall. Okay. Both of these equations can be used for Newtonian liquids and gases. Okay, so now let's look how to calculate pressure drop in pipe fittings. Okay, there are two methods to calculate pressure drop in pipe fittings. One is based on numbers of velocity heads. Okay, and the other methods is based on length of pipe to calculate the length of pipe that has same pressure loss as the fitting or the valve. Where for this length of pipe is a function of pipe diameter. Okay, now let's look at method one. So what I list those that I listed in this table is actually a summary of the step how to calculate the pressure drop in pipe fittings. Okay, so for method one, first we need to calculate the velocity head. So the velocity head here can be calculated by using the first term here or the second term. So the first term of the velocity head here, the unit is actually, let me write somewhere around here. Okay, this first term, okay, the unit is uh, meters of the fluid, meters of the fluid. While the second terms here, the unit is Newton per over meter square. Okay, and then after you calculate this velocity head, then we need to calculate the head loss. So the head loss is by multiply the velocity head that we get. Okay, where's my pen? Okay, the velocity head that we get multiplied by k, where k is the number of velocity head. K is the number of velocity heads. Then next we proceed to calculate the pressure drop due to the head loss. So we multiply the head loss that we get from the previous step, and then multiply with density and times with the gravity acceleration. Then at the end we calculate the pressure drop by adding the total numbers of velocity head loss. Okay, the pressure drop at the total number. This one is the pressure drop of the total number of the velocity head loss, and then plus with the pressure drop due to the friction. Okay, that's it. Okay, done for this method one. Then by method two, we need to calculate the extra length. Where is my point? Okay, my pen point. So extra length of the pipe to allow the losses. So how to do this? We total up all the equivalent pipe diameters for all fitting and valve. We can get this from handbook or any reference book, and then multiply with our internal diameter, and then we calculate the total length by adding the actual pipe length, to the extra length of the pipe. Okay, and then after that we calculate the pressure drop. Okay, the pressure drop due to friction. We're using the equation of pressure drop due to friction, and then we substitute with this total length. Okay, that's it. Right. So this is an example. It's just a small extraction from the original big table, I believe. Okay, because this is just a short list of the fitting of valve. Or fitting of valve. I'm taken from this book as well, Towler and Sinnott. Okay, this is my main reference for this lecture note. Alright. In order to get for detail of fittings, because pipe fittings is so many, and valve also there are so many types of valves, you need to refer related handbooks. An example is Paris handbook. Okay, and then let's look at an example here. Okay, in this example from this textbook, Chemical Engineering Design Principles, is quite good textbook. I'm going to show how to calculate the pressure drop that considering the friction and plus the fittings, pressure drop due to the fittings and valve. Alright, so here a pipeline, okay, connecting two tanks contains 4 standard elbow, a globe valve that is fully open, and a gate valve that is half open, and the line is commercial steel pipe. Okay, that's the information. Let we draw a line for information. Okay, they said there is a 2 tanks. Okay, with the 4 standard elbows, and then 1 globe. Okay, we have 1 globe. This one we have 4. We have 1. And then that is fully open. Okay, fully open, and a gate valve that is half open. And then the line is commercial steel, so we need to find a roughness for this. Okay, and this is the di. Okay, we have this di. All right, and then length is 120. Okay, this is our length, the actual length. This is actual length, so this is actual length. And the properties of the fluid, are viscosity 0.99, density, here we have density, so here we have this, and then here is our density, and then calculate the total pressure drop due to friction when the flow rate is this. Okay, this is our flow rate. Okay, now let's look the information that we have here, and then let's look, because while we in this PowerPoint, let's get back to this table. Okay, we have information of okay, we are going to use this table, this chart. I'm looking for the roughness. Oh, this one, this roughness. Okay, we are going to use this information, okay, because commercial steel part, so we are going to use this. Okay, commercial steel part. And then 0.046 millimeter, okay. And then we're going to find our friction factor, okay, as we are going to use this equation. Okay, we are going to use, I couldn't find my pen. Okay, this one. Okay, we are going to use this equation, right? And then for this chart, we need to find the friction factor. So what we have just now is our absolute. Let me write somewhere here. Okay, our absolute. Our absolute roughness that we have is 0.046 millimeter. So in order to get relative roughness, so what we should do is we should divide it 0.0 0.046 and millimeter, and then divide by our internal diameter, right? Okay, this DI. So our DI is 25 from the 25. Okay, is 25. All right. So then from this we will get 0.018, 0.0, okay, 0.018. So I'm going to round up to 0.02. Okay, so this is our relative roughness. So this relative roughness is somewhere around here. Let me draw the line, because it's going to be very hard to find. Okay, I'm going to double draw around here so that we can see easily. Later, just trace the line to help myself. Okay, I think should be enough time for here. Now let's recalculate our Renault numbers. We gather the information. We need to have U, okay? So our U is our U that we've been provided with flow rate. So our flow rate, I'm going to doodle around here. Sorry, it will look messy. We have flow rate. Our flow rate is 3,500 kilogram per hour. All right. So with this, we're going to convert it into velocity. Okay, we convert this to velocity. So our U will be 35. I divide 3,500. We divide by 3,600. This is to change into unit second. And then I divide by we need to calculate the cross-sectional area. Okay, when you need to calculate the cross-sectional area, so cross-sectional area, this is cross-sectional area, I get 0.491 times like 10 power of 3. Okay, this is cross-sectional area. You need to calculate the cross-sectional area. Okay, let me write somewhere around here. This is cross-sectional area. Okay, I hope you know how to calculate this. Okay, alright. Okay, this is actually cross-sectional area, as we already know our DI. Where is my pen going? This, we know our DI, so we can calculate our cross-sectional area. Okay, of the tube, cylinder. And then we need to multiply with 1 over the density. Okay, the density 998. Later you will get is 0.49 power of this -3 meter square. You get this. Not this one. Oh no, sorry for my mistake. I'm alright. Sorry. Where is my this? I need to. This is my mistake. Sorry. I need to erase this. Okay, I'm copy something wrong. I'm confused. What is meter square? Meter square is something. It's area. It's an area. Sorry for my mistake. Okay. My pen. Okay. Alright, sorry. Look at my note. I have to follow my note. Yeah, because I easily make a careless mistake. Okay, this is what I get. Alright, 1.98 as a fluid velocity. So we put it all the information in this to calculate our Reynolds number. So our Reynolds number 198 for the velocity times with the 25, okay, of the diameter in internal diameter. Alright, I change it into unit meter, and then time with density is 998. Okay, so the unit is meter, should be okay. Okay, make sure you check the unit so then it's easy to cross and you won't get wrong answer. I do not put the unit here because the space is so limited. Alright. So then the viscosity here from the question is 0.99. So divide by 0.99. So 0.99. Then I change the unit. Okay. So from here I get my Reynolds number is after rounded, I get this 5 times by 10. If we say 50,000 something, this is my Reynolds number. This is my Reynolds number. So from here, 5 times by 50,000, 50,000 Reynolds numbers. Where is my pen? The pointer is too small. Okay, somewhere around here. So this, we go straight. I'm going to show you how to read the Moody chart to get data from this. Okay, you get this, and then after that you projected this line into this, and then you get the amount around somewhere here. So I get the friction factor equal to 0.0032. Okay, this is my friction factor. Okay, all right. So we already calculate the U, we already calculate the cross-sectional area here, the Reynolds number. And then, all right. Then what next? Okay, then we already have know our F. Later I need to use my whiteboard. Let's look at this chart. Okay, where is it? Not chart, table. We need to select the fitting and valve that been listed in the question. So it said that it has somewhere of entry. The entry. So there's about entry to the tank. So I'm going to use the entry is 0.5. So we need to select which one. So this 0.5, I think the sharp reduction tank outlet, tank outlet, I'm going to choose this. Okay, because the outlet, the liquid from the tank, I think. The question, two tank contain flow standard, right. Okay, and then elbows, they have elbows, where elbows is standard elbows. Can you find the standard elbows? I find the standard elbows. Where the standard elbows? This. I think this standard elbows. Okay. 90-degree standard elbows. Standard 90-degree standard elbow. So I'm going to use the high range. And then this need to times by 4 because there are 4. It's saying that it has 4 standard elbows. Okay, we need to time by 4. And then it's saying that it has uh, globe valve open. So look at this. There is a globe valve. And then we need to find it. Whether it's bevel seat or plug this. Alright. So the globe valve that is fully open. So I'm using this. I'm consider it's bevel seat. I assume it's bevel seat. Then this is fully open as if been listed, be specified in the question. So this 6. How many valve are there? Only one. They said it's a globe valve, so only one. And a gate valve. Where is a gate valve? Somewhere around here. A gate valve. And it said the gate valve is half open. So this is half open. Okay, 4. So I'm going to use this 4. Okay. This also. Okay. And then exit. So we have exit. Okay. Alright. They have exit. So we choose this. Okay. Tank inlet 1. Exit of the tank 1. Exit, this is exit of the pipe, I think. Exit of the pipe. Alright, sorry, exit the pipe. So I mean the water come in, pump in into the tank. So we were going to take this K number 1, and then with this and this value, you need to total up it. Okay, total of this you will get 14.7. Okay, 14.7. And then same thing here, the equivalent. So we are going to refer at this 40 times 4. Okay, 40 times 4. And then we have 666. Where is this? We have where are you? We are going to use this, or is it this? Standard action. Yeah, right. And then this value of this we're going to take, and this one. Okay. So adding up all this, we're going to get total of number of equivalent pipe diameters equal to 735. Okay. Okay, keep it safe. Okay, hope you remember this information that I'm showing in this table. So now let's look the method 1. Okay, to solve the equation. Okay, to solve this equation, this question. Okay, this question. So I'm going to share my whiteboard. Okay, I share my whiteboard. Okay, so for method 1, oops, I already shared. Where's my whiteboard? Okay, share my whiteboard. Okay, so for method 1, all right. So we need to calculate a velocity head. A velocity head. We already calculate the velocity just now. So I'm using this equation. But there are 2 equations for velocity head. You can check my slide later. So I'm putting the information that I already calculated previously. And then times by this, you will get 0.2 meter of liquid. This is the unit. Alright. Then we calculate the head loss. alright, is equal to 0.20 times 14.7. Okay, 14.7 is the K, the value of K. This one is K. Alright, hope you remember this. And then this is the velocity head. And then we will get 2.94 meter. So then change this head loss into pressure as pressure. Alright. So I can say this is the drop due to head loss. So we can guess a pressure drop due to head loss. So we have 2.94 times by the density times by the gravity acceleration. You will get 28,754 and over meter squared. So then now we calculate the pressure drop due to friction. So the equation is 8 times by F L over D I rho U over 2, and then we substitute the value 8 times by the F that we get from the Moody chart. Alright, the length of our pipe 120, 25, then times by the internal diameter. Alright, this, and then times by the density, times by 1.98, then divide by 2, you will get, what is it, 388 Newton per meter squared. Alright, now we need to total up. So the total pressure, okay, I put the total pressure will be, okay, we add up this and this, okay, plus, so you will get 270 K Newton per meter squared. Alright, that's it for method 1. Right, for method 1. So my whiteboard is a bit small. So I need to, can I save this? Okay. Alright, and let me save this. Save as PNG. Save in folder. Okay. Alright, done. Then then we save. So then I need to erase. How to erase all? Or can I use? Okay, just erase. Okay, now let's look on method 2, yeah. For method 2, okay, so for method 2, so now we for method 2, okay. So for method 2, we use the to calculate the extra length. We need to calculate the extra length. Where's my whiteboard? Okay. All right. So the extra length that is needed is actually 735 times by di times okay, di. So this di is 25. This one and then you will get 18.4 meter. So we need to total length, to calculate the total length is actually our actual length is 120 meter plus 18.4 for the extra length that we needed. Okay, so we can get 138, we will get 138.4 meter. This is the equivalent diameter that we get in the table. I showed you how to calculate that by selecting the all the related fittings and valve involved in our piping system, right? Then after that, we use this information of total length, and when we substitute onto our pressure drop due to friction equation. So 8 times by 0.0032 is our friction factor from the Moody chart. Alright, then we insert our new length here. And then is 25 times 10. 3 is our internal diameter, multiply with the density, multiply with the 198 1.98. Okay, 1.98 is our fluid velocity. Then divide by 2 and we will get 277.247 Newton per meter squared. Alright, that's it. So basically, this is a method 2, and method 1. Just now, from method 1, we get our data P is 270 kilonewton per meter 2. So basically, it's not the same, right? It's not the same. But of course, the method using velocity head just now is the more how to say, more correct approach. But the use of equivalent diameter by finding the extra length here is more easier. The step is a little. The step of calculation is not so much compared to method 1. But both method are appropriate, and if you would like to use method 2 also is appropriate also, and is sufficient also for preliminary design. Okay, now let I share you my PowerPoint slide just now. Okay, so that is the example. I hope you can do it by yourself later on. Okay, so before I end this video, I would like to share these rules of thumb to minimize pressure drop. Alright, these rules of thumb is actually from Central State Industrial website. Okay, they list things that process engineers should do in order to minimize pressure drop, which are by ensuring the process pipe's interior diameter and the size of the pump are properly sized for the type of fluid that's being piped through the system. So any mistake can result either excessive, any result mistake can result at the excessive pressure drops or over pressure situation. So and then another thing is we need to minimize the number of additional mechanical components. Okay, example like valves, flow meters, adapters, and couplings in a process pipeline, as all of these can add to problem with pressure drop. And we need to also to ensure the process pipeline is laid out to be as compact as possible. Okay, this is to minimize the pipe lengths and bends, and make sure that the process pipeline as level as possible, as changes in piping elevation in the pipeline system will contribute to either pressure drop or overpressure situation. But of course, we need to have a little bit degree, just more degree to allow fully drainage. When you want to do a drain, you want to drain the liquid from the pipe is easy. That is under hygienic consideration. Okay, okay. So, okay, I hope this video provides useful knowledge to you. And thank you for watching. Bye.